Here's our first video for Lesson 31, Systems of Equations. Our objective is I can solve systems of linear equations in two variables and systems of a linear and quadratic equation in two variables. I can identify that the points at which two graphs of the equations intersect correspond to the solutions of the system. So we're going to find where these equations intersect, and that's actually going to be our solutions. So number one says sketch the lines given by x plus y equals 6 and negative 3x plus y equals 2 on the same set of axes to solve the system graphically. So the hint is to rewrite both as y equals mx plus b, slope-intercept form, then solve the system of equations algebraically to verify your graphical solution. So these equations in slope-intercept form, so our first equation is x plus y equals 6. So slope-intercept form, y equals negative x plus 6. So we have a slope of negative 1 for that one. So slope is, just as a reminder, is your rise over your run. So that means that goes down. Negative 1 means you go down 1 and then over 1. Our second equation, negative 3x plus y equals, should be a plus there, equals 2. So that becomes y equals 3x plus 2. So this one has a slope of 3 and an x-intercept at 2. Our first one had, a y-intercept at 2, and our first one had a y-intercept at 6. So now I'm going to plot these points. So the first one, I know I hit at 6 right here, and I go down 1 over 1. So I have a negative slope, and my little stylus is being kind of difficult, but that's the equation right there. For my second one, I have a slope of 3, so it's going to go up 3 over 1, up 3 over 1, and it hits at y equals 2. So there, and I'm going to go up 3 over 1. That's an intersection point right there. Okay, so they intersect when x is 1 and y is 5. That's the solution for those two equations. Now, if we solve this algebraically, remember how we set them up in slope-intercept form? Over here, y equals negative x plus 6 and y equals 3x plus 2. So when we're solving them algebraically, what we're looking for is when do those two equations occupy the exact same space? When are they equal? So they're equal when negative x plus 6 equals 3x plus 2. So now I'm going to solve for x. So I'll add x to this side, I'll subtract 2 from this side, and I get 4 equals 4x, x equals 1. So when x equals 1, I'm just going to go ahead and figure out my y value. Y equals negative x plus 6, negative 1 plus 6, y equals 5. So my solution is, again, x equals 1, y equals 5. Okay. The second equation is you take the first equation, the same one, and I'm going to just do this in a different color. So, okay, but our second equation has changed. So our first one is still y equals negative x plus 6. And our second equation is y equals negative x, plus 2. So when we plotted our first equation, it went through 6 and it had a slope of 1, so it dropped down like that, or negative 1. Our next one is going to go through 2, and it also has a slope of negative 1. We've actually created parallel lines. There's no solution there. They never cross. A solution is where they intersect. And let's see if that holds true algebraically. So we're going to set the two equations equal to each other. These were our two equations. We're going to set them equal to each other over here. We're going to say negative x plus 6 equals negative x plus 2. Well, our x's can cancel out. If we add x to both sides, it goes away. And then we get 6 equals 2, which is no solution. 6 does not equal 2. Okay, our third one is we're going to start with our original equation, y equals negative x plus 6. But our second equation has changed to 2x equals 12 minus 2y So I'm going to just set that up in slope-intercept form. So I'm going to bring my 2y over here, add it to both sides, negative 2x plus 12. Everything's divisible by 2, so I get y equals negative x plus 6. And you might notice those are the exact same equation. So if I graph the first one, and then let's say just for kicks that I graph the second one in red, it's going to occupy the same space. And that's because when you solve them algebraically, negative x plus 6 equals negative x plus 6, that's true for all real numbers. Okay? So that's why everywhere on here, they're a solution. It's true for all real numbers of x. So the solution is there's infinite solutions. It goes on forever. So what we just found is that a pair of lines can intersect in 1, 0, or an infinite number of points. Those are the options for a pair of lines. But now let's add some different shapes. Now let's look at what about with a circle? Well, we have a couple different options. If we go through right here, it can intersect in 2 points. Okay. If it just hits right on the side, that's called a tangent. That's 1. Or if our line is out here and our circle's up there, 0. So a line and a circle can meet in 0, 1, or 2 different places. Okay, how about a parabola? Okay, a parabola and a circle are both considered quadratic equations. They have x to the second power. So for a parabola, okay, we can go through here and here. That's 2. Again, we can have it hit, oops, that's not very good. We can have it hit on a tangent, that's 1. Or our line can be out here, 0. Okay, so those are your possibilities. For question 4C, it says, using decimals, graph the circle x squared plus y squared equals 1 and the line y equals 2x plus 2 together. One solution to the pair of equations is easily identifiable from the sketch. It's whole numbers. What is it? Sketch the circle and line below. So if you go on decimals and you put in x squared plus y squared equals 1, what I know from this is that my since the formula for a circle is x minus a squared plus y minus b squared equals radius squared, a and b are your distance from 0. Okay, so it's just plain x squared and y squared. So there's no distance from 0. So this is meeting at the origin is its center, and it has a radius of the square root of 1, which is 1. So I'm going to draw my really ugly circle here. I'm kind of bad at drawing circles here. Close enough. Okay. And then when I draw the line y equals 2x plus 2 on here, I know that it goes through, boom, right here at negative 1, 0. And it's also going to go through right here. And we're going to figure that point out algebraically in just a second. So this is what you should have for part C. Now let's look at part D. It says to substitute y equals 2x plus 2 into the equation x squared plus y squared equals 1 and solve the resulting equation for x. So anywhere we see y, we're going to plug in that. So we have x squared plus 2x plus 2 squared equals 1. So x squared, and now we have this perfect square trinomial. 4x squared, 2 times 2x is 4. You double that, you get 8x plus 4 equals 1. If I combine like terms, I get 5x squared plus 8x plus 3 equals 0. Let me factor that. 5 times 3 is 15. They have to add up to 8. Well, that's a 5 and a 3. So I have 5x plus 3, and then the 5x plus 5, but those can both simplify out by 5, so I get x plus 1 and a 5x plus 3 are my binomials when I factor this out. So that means x equals, that equals 0 when x equals -1 and when x equals -3/5. Okay. So what is your answer to part D? Tell you about the intersections of the circle and the line from part C. So the intersections of the circle and the line from part C occur when x equals -1 and x equals -3/5. And if you look back at your graph on Desmos, you should see there'll be a point at 0.6, and then 2 times 1.2, and y would be, I'm trying to do the math in my head right now, my brain is not working, so y is 3.2, should be. Okay, so the intersections of the circle and the line occur when x equals -1 and x equals -3/5. Okay, we proved it algebraically, and we graphed it on Desmos, and it showed us that's actually where those intersections were.